kind of in generalized sense. I mean, it's not connected, so. And this is due to, it's a combination of theorems of Bailey, Borel, and Borel. I'm just sitting here. Sometimes I write this and I'm in the system for all K, so if you're worried about the canonical. And then, of course, a major theorem is that not only you have this, but you also have a canonical structure. So a so-called canonical model over the reflex field, which is, as I said, the number field. And this is due to many people, Shimura, Deling. The final kind of cases were done by Milne and Borovoy. Okay, so the talk is about the question. Here's right here. So the question, is there a canonical integral model? So integral means, well, integral model would be a scheme over the ring of integers. Of the reflex field. So that's what we're trying to figure out here. Well, a priori, there's no reason to expect this. I don't know, in general, because Shimura varieties are mysterious somehow. They're still mysterious objects, and there is a kind of a guiding philosophy that they should be moduli of motifs with values in whatever group you picked. But in practice, the reason why we're successful in studying them so far has been because we can express them through moduli of abelian varieties. And so the motifs are actually abelian varieties with additional structure. And this leads to the following kind of a range of, or kind of hierarchy of difficulty. So first you have the things that are exactly moduli space of abelian varieties, say with principal polarization, the Ziegel-Shimura varieties. This is part of a larger class that are often called PEL type, in which you look at moduli of abelian varieties with polarization, endomorphism, and level. That's initials. Then you have the so-called Hodge type, in which you are allowed to have other tensors that are not endomorphisms of polarizations. They're higher Hodge tensors. Then usually people use the term abelian. And finally, you have the general ones. So this is the whole set somehow. So here, you have the exceptional groups. There's only two types of exceptional groups, and some orthogonal, some kind of twisted orthogonal groups that show up. And from here and on, you cannot really express things in terms of abelian varieties, but here you kind of can. And in fact, like up to here, the Hodge type can be embedded in the Ziegel type. So you can look at them as subvarieties inside the Ziegel moduli spaces. But even if you get so far, you can go to the abelian types by some kind of Gaussian construction. So everything up to here can be accessed with abelian varieties. This is the Wild West somehow. But there are not that many down there, so we don't care so much. I mean, that's the idea. Okay? And so our only kind of course, between, so from here to here, there's not a lot of conceptual difference in studying them. You just added homomorphisms or something. From here to here, there is a big difference. You need to use like Hodge theory, which is more advanced. From here to here is like just combinatorics in the group, and here nobody knows what's going on. So, yeah. So that's kind of the idea. And the results for integral models are basically, they're all obtained by the technique. you take something from here, you embed it in the Ziegler space, you take Zariski closure in some Ziegler embedding, and then you try to study what's going on. So Ziegler space makes good sense as moduli scheme over the integers. So that's why you can kind of do that. Of course, taking Zariski closure is an operation that you cannot control very well. So you have to work hard to figure out what's going on. So this is the basic idea every time. And so there are now another kind of range of difficulty in what's going on and what you see that depends on the prime you choose to study the variety over. So let's do some notation. I use a place, take a place of the reflex field. Let's say V is over a rational prime P, and I'll use some notation. Here's the completion. I have the integers. Sometimes I'll drop the V because I'm talking always about the same thing, and then say the residue field, which is a finite field. And then I'll use K to be an algebraic closure of that. OK, so everything depends on what happens at P. So we also kind of choose the notation that the level subgroup is this. So I kind of distinguished in the notation the choice of the P part. So here, this is in here, and this is the rest. Right, the prime to P and the P part. And things depend on these choices. So, OK, so you have the good places, V, say, over P. And these are when Z extends to a reductive group, group over ZP, and we pick KP to be the ZP valued points of this. This is the so-called hyperspecial case. In this case, we expect a smooth integral model over OV. And in fact, Milne has given a characterization of this in terms of some extension properties. So there is a kind of notion of canonical that's like, I guess, 30 years old. And so there is a good notion of canonical. And it's a theorem of many people. And the final kind of thing is by Kissin, I guess, before there's work of Vascu. That says that this is OK, this exists in the abelian case, abelian type. OK, so OK, so now we're going to get out of the good case and consider. Yes, I can safely erase this. Bad places, but one realizes that the situation is pretty hard in general, so we're just going to restrict, at least in the talk, and in everything I know, by the way, to the so-called Paregoric places. So I'll have to explain this. Paregoric places. So these are not good. You expect bad reduction, but it's like, in some sense, tame reduction, tame bad reduction. So here, KP is a Paregoric subgroup, and I'll explain what this is, or GQP. So what is a Paregoric subgroup? So you have the group, Piali group acts on the Bruchatitz building, let's write it this way, B of G, the Bruchatitz building, And if you take a point in the building, then Bruhat it's associated to this canonical smooth group scheme over the p-adics with a property that the points, GP valued points, are a stabilizer of a point X in the group. Now, so this is almost what a Paregoric subgroup is, but not exactly. So what you do is you take the neutral component of that group scheme, and then you say that Kp is Paregoric. So basically are the points of these neutral components. So the definition is that there is an X in the building such that Kp is the ZP points of that guy. And in what follows in the talk, I'll use this notation. So this group scheme, I hope that this is clear, like this weird calligraphic G. I'll use a lot in what follows. All right. Okay, so great. So here's some examples so you get a feeling of what are these Paregoric things. Of course, any subgroup, any group, when the group extends to a reductive group and you take the ZP value points that we've seen before, this is Paregoric. So we recover the previous kind of cases. But there's two more central types of examples, I guess. So one is the following. There's 3 boards. Example. So let's say G extends to a reductive group over ZP. And now I can do the following. I can take, I denote the extension the same way, take Z points such that Z mod P, if I reduce mod P, this belongs in some parabolic subgroup. So this is some parabolic of this guy. And then this would be an example of a Paregoric subgroup. Another example is if you do this, think of your group, imagine your group is a restriction of scalars for some maybe ramified extension or something of some other group, and the G prime extends to a reductive over the ring of integers of the top field, then you can take Kp to be this, the off-valued points of G prime. So you can get the ramification this way. And so these are the two kind of central examples in some sense. The point is there's always a Paregoric subgroup. That's important because there's not always a hyperspecial subgroup, but there's always for any group a Paregoric subgroup. So if you want to study the star Shimura varieties, you can start someplace always if you kind of include this case. So there's a place to start. Okay, so what do we want from our models? So we want to construct these models, right? So, or the system. So I'll denote them by this calligraphic SK. So K varies, but since we're sticking with this case, it's important to pick the P level fixed, right? And so we want to have this over the integers. Okay, so bad choice. Maybe I should go up there because I need to keep some of these properties to stay. So here's some of the properties we want somehow. And they're like soft and hard. So, there are a couple of soft properties that we want. This to be, say, flat over O. And to be really a model, this means if you look at its generic fiber, is the Shimura variety. And stop writing GX, of course. So you want the Hecke action from the generic fiber to extend. So if you have two subgroups, but now you only want to prime to P Hecke here. This goes, say, here. You should have a map from this choice to the original choice that, say, finite et al. And that which extends the corresponding map you have in the generic, over complex numbers or generic fiber. So I'm not going to write that. This property is a little bit kind of surprising. Relative properness. Maybe I put a P here, so I referred it. Okay. This says the following. Oh, before I say that, maybe I'll introduce the following notation. I'll write S with just the P part to be the limit, projective limit, where I let all the other guys go, go to infinity somehow. So the limit is over the prime to P stuff. So this makes sense after the assumption too that this is a finite et al. Map, so you can take this limit, it kind of makes sense. Right? Okay. Well, these guys, so the relative properness is the following. For every R, some dvr flat over O, I ask that the R-valued points of this is the same as the points of the Shimura variety of a generic fiber. So the way to read this is every point of a Shimura variety or the tower of this Shimura variety extends to the close point of the dvr. So it's like a properness criteria for this tower. Okay. So this is kind of important. It avoids you cheating. So you're trying to construct these models. You can always make them nicer by throwing away unpleasant stuff at the spatial fiber. But we really don't want to do this. We want this to be as proper as possible. That's the meaning of this condition. Still, these are the soft properties. And maybe now I'll return. Okay, I kind of omit this board in my rotation, basically. So, okay, so some hard properties. What can you predict with some confidence? Even though you can't prove, right? So the first thing you can predict is like, now these are hard, I'm not going to stick with them, I'm just not going to number them. So you can predict how the points with values in finite fields should look like. So take this kind of tower again, and take the k-valued points. Remember, k is the algebraic closure of the residue field. And so this has a prime to P Hecke action, and also it has the action by the Frobenius. So you have these two actions, and you can actually make a prediction for how this set looks like. This is really difficult, and it's the content of a Langlands-Rappaport conjecture. And it's useful for trying to understand the L function of the Shimura variety. I'm not really going to talk about this anymore in the talk, because my kind of, I'm concentrating on the other thing we can predict, which is the local structure. And actually, I mean formal local structure here. Okay, so, Okay, let's make this so-called Serre assumption on the center here, which means that the maximal, so assume the maximal R-split torus of the center is isotropic. Just to keep me honest, you can forget this if this is too dense. Oh, yeah, the center, I wrote this. And then you have a so-called principal automorphic bundle, which is a G torsor over the Shimura variety. And this supports a map into the compact dual of the domain. Now, the compact dual of the symmetric domain is some homogeneous space, which is really the variety of parabolics of type mu, where mu is this Hodge character that came from H. And so you have this triangle where you have a G-action here, because this is a torsor. You have a G-action, of course, here. And this is equivariant and actually smooth. We'll see the significance of this later. OK. So the way to get this star of the complex numbers is just use the Borel embedding and these double quotients that go everywhere. And the way to understand this map is this gives you the variation of the Hodge filtration. Somehow the values in here give you the positions of the Hodge filtration after you trivialize the bundle, right? And so actually this was shown to have a model over E that's compatible with the canonical models for the Shimura variety. This has a model over E also by Milne. Okay, so this is, I didn't say anything about the integral structure yet, but the point is that this should extend. Maybe I write it here. So the expectation is that this triangle should extend to something over the integral model. So where you have a G torsor now, this is my group scheme that was given by Bruchatic, and this map should be smooth and G equivariant, where, I didn't tell you anything about this, where this is a canonical model of the compact dual, canonical model over O of this variety of parabolics of the compact dual. Okay, so what does canonical here mean? It means that I will tell you how to characterize this. And so somehow I'm making progress about saying what the canonical model of a Shimura variety is by telling you first what is the local structure of it. So I have some canonical local structure at least after I finish stating this. Okay, so okay, this M is a so-called local model in the theory, and I will try to list properties that almost characterize it and then tell you about how to actually characterize it. So what this should be, should have a G action. Of course, I kind of already used this because I talked about a G equivariant map. Should be depending only on the local stuff. So the local stuff here is the level at P and the mu. And some further properties. So let's try to list those properties again. I call them A, B. So M is flat. This is some dummy properties over O. B, of course, I already said this. I'll write it though. If you go to the generic fiber, you really get the compact dual, and this is equivariantly, right? And now here comes some more difficult things. So the special fiber should be reduced. And in fact, I can tell you what are the points. So I kind of know this generic fiber, and I know the special fiber, more or less. So it's reduced, and I can tell you the points. The points are, well, I can't really tell you. I can give it a name. So that admissible set. So it has a combinatorial description inside the affine Grassmannian where, okay, we'll meet this again, but these are the Witt vectors. So this is a lot to absorb if you're seeing this for the first time, but I mean, the point is that this is a very combinatorial description of this, as there are union of supercells in the Grassmannian. And so you know the special fiber, you know the generic fiber, you know the special fiber is reduced, and you should think, oh, maybe this fixes the model completely, and I guess that's the conjecture. Oh, maybe I add another one. So it should be functorial, and now this you think it should fix. Functorial and invariant under central extensions, because meaning if I change the group by a surjective map whose kernel is central, then I should not be changing this variety, right? The same way as you're not changing the homogeneous space when you do this. And now you should think that this characterizes the thing uniquely because you're fixing the generic fiber, special fiber. You're saying the special fiber is reduced, so there's no funny business kind of going on. And I guess that's the conjecture, but we can't prove this. We can't prove that there's only a unique scheme that has these properties. However, Solze found a way to characterize it using his B sieves. So I'll tell you a little bit about that. Before I go. Well, actually, I won't tell you a lot about that because this will involve saying a lot more things. But so Solze creates a functor from schemes of this type, like flat and normal over a DVR, to sieves in perfectoid spaces. And in perfectoid spaces, you can make sense of quotients like this more generally, not just for K, but for more general rings R. Maybe they're perfect. And this gives him a way to get the R-valued points there. So he kind of generalizes this property to more rings, and this allows him to kind of determine the corresponding this sieve. So there's a functor from schemes like that to these sieves, and the functor is fully faithful. So if you know the image, you determine, what you had. But you can't solve it. There is something on this end. So meaning, if you have this, you can prove you can characterize it, but you cannot construct it by Solze's methods. So let me write something. So Solze constructs. I'll just write this for completeness. This sieve M diamond is not really a diamond in his terminology, but almost. So, and this can be used to characterize M if this exists. But it is a kind of a good situation because actually we can show that these things exist. So there is a construction of M in many cases by me and Xu and Zhu and Van Levin. There's more people here, but basically, like also he, myself, and Rappaport that tells you that this is okay. You can have such an M that also satisfies this Solze characterizations in most cases. What do you mean most cases? You exclude some groups for small primes. For p equals to 3, and you have to be in the Hodge type case. Well, maybe you can do the abelian type case, but I'm not sure. So this is like, the situation is good. So we know this. That's the bottom line under what the local structure for this. Now this is not a pie in the sky type of conjecture, because there is a result that tells you that the local model works. Let's call theorem 1 by Mark and myself, that says, let's do this a little bit carefully. So let's assume first thing, Gx is of Hodge type, and second, that I have a lot of unpleasant assumptions, but okay. So splits over a tame extension of QP. What else? P is odd. P does not divide pi 1 of G derived. I mean, actually, I'm not sure if this is needed. And finally, this, that the Bruchatit scheme is already connected. So I assume all this. Then there are models that satisfy all these things here. So I call this LMP, so a local model property. So with the 1, 2, 3 plus local model property. This, no, I can't. Or maybe somebody can, but I can't. So yeah, it is annoying, but all right. So this is not an unrealistic thing to ask, and in fact there are other indications why this local model, especially after given Solze's description, is the correct one. But now this is not what I promised to talk about somehow. Not just the construction, I promised to kind of explain why I think this is canonical. So canonical means I have to characterize it in some way, right? And so this, we're not there yet, but so I'll have some. So canonical. So are these guys canonical? What does this mean? Canonical means I give you kind of a list of properties such that every model that satisfies these properties is isomorphic to, every two models are isomorphic to each other, right? Okay, so what are these properties? Well, you can, a good guess is you take 1, 2, 3 plus this, and that works. And maybe that's true. I just don't know how to prove this. We don't know how to prove this. Only in few cases we can do this. I mean, it seems like this rigidifies things a lot, actually, but I just can't prove it. So, on the other hand, there is something else that seems to work. And
so
yeah.
So Scholze suggested something.
Yes.
Is what he suggested a characterization?
Is characterization of the local model.
Of a local.
Yes, exactly.
And you wanted
But now we want to go from the local model to the whole Shimura variety. So this is a good step. I mean, that was my point. I mean, the Solze's characterization of the local model is a good step, I think. But we're not there yet. So to talk about this, I have to talk a little bit about G mu displays. So the idea here is that this kind of fixes the formal local structure, and if you believe that this is a moduli space, it's like you're fixing the deformation theory. But I want a little bit more than that. So I want to fix the objects that give you the deformation theory somehow, and these are the displays. So in some sense, these are the crystalline avatars of the G motifs, if you like. So to explain what this is, I have to tell you about the so-called binary classical displays invented by Zinc, which are like fabulous objects. So I'll make some assumptions to make the discussion simpler. So prime is odd. R is a complete local Noetherian ring with residue field. In general, perfect, but I might as well assume it's my case, the algebraic closure of the field. Now I need to talk a little bit about the ring of Witt vectors without a lot of details. So these are just sequences of elements of R where the multiplication is given in this weird way by ghost coordinates. I'm not going to do this now. I'm not going to explain this, but these are the ring of Witt vectors. I mean the p-typical Witt vectors, for those who know. And this has two maps. The Frobenius, that I will denote by phi, is breaking a little bit with standard notation, and the Versibuk that I will denote by v. So phi is a ring endomorphism, v is not. But the formula for v is very easy, so I can tell you this. So you just push things back. You stick a 0. That's the v. And they said another useful thing I can tell you that's easy is that if you can compose them in this order, you get multiplication by p. Okay. So these are the Witt vectors. And okay, maybe I'll write here a little bit. And so here's some more stuff. Now, under my conditions, I can split. This is important to have these conditions. I can split this ring this way. So it's a direct sum where these are the Witt vectors where the coordinates are from the maximal ideal. Right? Now, and inside this guy, I take, so this is a construction due to Zinc. I mean, it's all this due to Zinc. So you take this part of a direct sum where this is the subset of these guys where the elements go to 0 in the emmadic topology. So meaning they belong in higher and higher parts of the maximal ideal. And so you can write this direct sum by W hat. And it turns out that this is also a ring, and it's also fixed. It's stable under the actions of phi and v. So it has all this data itself. Right. Now this uses the fact that p is odd, for example. Okay, so maybe I can get rid of my stuff here. Now, so now what is a display? Or rather, more technically, I would say Dieudonné display in Zinc's terminology. Oh, I'm not there yet. One more piece of notation, sorry. I want this, the image of the Versibuk operator on W, let's say W hat R. So just starting with 0, this is an ideal inside W hat R. And if you take the quotient by this ideal, it's just, you're looking at just the first entry, and you sort of recover the ring R. So it's isomorphic to the ring R. Okay. All right. So what is a Dieudonné display after Zinc? Over R. I'll stop writing and saying Dieudonné after this. So it's a triple where, so M is a projective in general, but here everything is local, so it's a free module of some rank. M1 is some submodule that sits between here and here. So So it's like a filtration. And F is a map from M1 to M. And they should satisfy the following axioms. First, the quotient. This quotient is a module over this quotient. So it's a module over R, so it should be 3. Which am I doing? Yes. Say of some rank D. And then I have some weird identities the first time you see them. If you don't know where this is coming from, it's just bizarre. But actually it's not bizarre after you see where it's coming from. So you have this kind of identity for A in the width ring, and M1, of course, in the module M1, and also this one. And finally, you ask, okay, this is at this point that I've lost the audience, but that the image of F generates the module M. Okay, so there's these technical models. If you've seen Dieudonné here, you'll recognize some of this. I mean, and why is this interesting? Well, it's interesting because of this beautiful theorem of zinc that says that there is a equivalence of categories essentially between P divisible groups over R and this displays over R again. And now to be here, I gave you these numbers N and D. So if I keep these numbers the way they look, this corresponds to P divisible groups of height N and dimension D. So this is making P divisible groups into linear or complicated linear algebra. So it's very good, I think. So, yeah. Okay, so in order to kind of give our characterization, I need to talk really quickly about the version that I promised where I said Z mu displays. So the zinc displays are essentially displays for the pair GLN mu D, somehow, where this is the co-character that gives you that, the minuscule co-character GLN that corresponds to this dimension. And so there is a generalization. So what are those? Displays. And unfortunately here there's a technical glitch. We need to assume some more stuff, that R is normal and flat over ZP. And this might look like a small detail, but actually makes life really hard. So these are, again, triples. But now I have to rephrase everything in terms of torsors for the group instead of lattices. So here, P is a G torsor. So these are over R, right? Over W hat R. This is really strange. I want a equivariant map from the torsor reduced modulo I to the local model. Now the local model only depends on G mu also, as we were saying before, so this makes sense. The local model was depending on Kp and mu. Kp and G are the same thing somehow. And, okay, you might wonder how does this connect to this? Okay, it's not very so obvious. And then finally, F is kind of harder to explain, but what you do is out from here, from this gives you some sort of filtration, and out of the filtration you get a new G torsor. basically this new G torsor is like corresponding to the M1 in this language. And now you ask for an isomorphism. The third piece of data is F is an isomorphism of G torsors from Q to P. So it looks like something is off, but actually it's not. It's kind of difficult to explain why they are equivalent, but I'm promising you that in the case of GLN, you can recover exactly the previous setup by doing this. This one. Yeah, I can. You're right. Yeah, I can talk to you afterwards if you want. What?
Is this a definition from a published work?
No, this something is what I'm writing. I almost wrote it. Yes. So yeah, that's right. So there is this definition, and as I said, for GLN you get the same thing, and maybe now it's time to sort of cut a long story short to state some result. Okay, so say theorem 2. So the same assumptions as in theorem 1, which probably nobody remembers, as theorem 1. You're still there. Okay, great. Okay, that's great. I thought it was all gone. So same assumptions as theorem 1. And then, okay, so the first thing is these G displays, they are natural G displays over the Shimura variety. So for every close point of a special fiber, geometric close point, there is a G mu display over the completion of the local ring, which is, okay, now I'm going to say some terms that I probably won't have time to explain, but which is first versal in sense of deformation theory of these objects, if you like, and again some term that I won't explain if there's no time, associated to the étale cover, actually pro-étale, wrong choice, KP cover. So here's what I want to do now. I start with a mod, now this, no, the variety, because this is over the generic fiber. This cover is over generic fiber. And then I take the limit where I make the level at P now shrink. Now I fix this guy and make the level at P shrink all the way to the identity, if you like. So if you do this, you get the successive covers are by quotients of this type. And when you go all the way to the limit, you get a pro-étale cover for Kp, right? So you can think of it as a sort of a p-adic Galois representation that lives over a Shimura variety. And there, okay, so this is the first part of the result. And then the second is that if you have if you have another system of models that has this gadget over it, it has to be isomorphic to that first one. So part B, if you have two guys, let's write it this way, models of the Shimura variety satisfying these properties. Now they're still there. No, these are gone now. 1, 2, 3, and so this is something stronger. The local model property, and I have this data and support this data as in A. They are isomorphic. Of course, they are isomorphic by an extension of it, like the identity of the generic fibers. I mean, if you okay, so this is the corollary. If you put those two together, essentially it tells you not essentially, that the models of firm 1, now this is gone for sure, are independent of choices. And so you can call them canonical. Although I have to admit that this is kind of a weak success here. I mean, because this property is too elaborate, in my opinion. So I want to find something simpler than asking for this system of things. For example, it would be nice to have a whole display over a whole Shimura variety, not these things over the formal completions. Now, the theory is not strong enough to kind of handle this, apparently. I mean, at least I don't know. So maybe there is still 5 minutes. I can try and tell you a little bit more kind of precisely what is maybe associated or versal, and maybe the proof. I don't think we'll have time, but maybe I tell you versal. I think it can be understood a little bit easier. How about associated? What is associated here? I mean, the whole the technical part of all this construction is to make this work out right. And this is the hardest part, where we pay all the price. So what do? You have this Bruch-Hatitz group scheme. You want to embed it into GLN for some n in a good way, so that the character mu here becomes one of the minuscule characters for GLN. And this you can do under the Hodge type assumption. Okay, so you have this. Now this tells you that every time, after you do this, every time you have a G mu display, this will produce you, just by factoriality, a display for this pair. But as I was trying to explain, this is the same as this zinc display of height n and dimension d. And so this is the same as a p-divisible group of height, the same stuff, height n dimension d. Now, when you have a p-divisible group, so this leaves over R. So R in my game here is this formal completion of my Shimura variety at a point. So I can look at the Tate model. The Tate model over the generic fiber of this. So some rigid space, if you like. So, okay. So what is the Tate model? A way to think of it is a local system. So Zp to the height is n, Zp to the n et al. Local system. And now you can use this local system to create this cover of trivialization. So you get out of this the GLN Zp cover. Okay, so great. So this is for GLN really. So we started with G and we produced some et al. Zp to the n et al. Local system, so a cover for GLN. I want to reduce this to a cover for the group Z ZP. Now, this is all the difficulties in doing this. And the reason why this is difficult is the way to think of this is the following. You view Z as a fixator, stabilizer of a bunch of tensors inside ZLN. And now, when you're looking on this side, it's like having the tensors given in the crystalline theory, because they're supposed to be Frobenius equivariant, they respect the filtration, etc., etc. And now you have to match them with tensors that live in the étale world. So somewhere there's a comparison between crystalline and étale, and it has to be at the level of integral, at the integral level. So this is what makes this hard, because you need some integral p-adic Hodge theory, and this is provided by essentially two ingredients, Kissin's modules and the work of Butt, Solze, and Morrow on p-adic integral Hodge theory. So you need to, it's kind of technical, but to make this match and show that the notion of associate is also independent of the choice of the embedding is some hard work. So, but after you do this, then the rest of the proof is actually kind of easy. And okay, I guess maybe I can say something about this really, really quickly. So if you have the setup, especially the independence of the embedding, then things are not so hard. So let's discuss the proof of, say, just one word about the proof of B. B is up there. If you have two models that they're the same, right? So you can put yourself in a situation where you have those two models, and somehow you can even manage so that they're connected by a map. If they're not, you make a third one that kind of maps into them by triangle by some closure. So let's assume there's actually a map, right? And so they both have the same generic fiber, which is the Shimura variety. And so now I have this map between them. Let's try to see what I know about this map. So these two guys are both relatively proper, and they have the same generic fiber. You can see that this map has to be proper. So then these two guys have local structure that's determined by these local models. But these local models have a reduced spatial fiber, so they are normal. So both of these guys are normal. Okay, so now what do you do? So you have one versal p-divisible, one versal display here and one versal display here. You can look at the p-divisible groups. Now, but they are associated to something that lives on the generic fiber. On the generic fiber, they are the same. So if you pull this guy up to this, you get the same thing. So the pullback of the G mu display from this guy is isomorphic to the G mu display that lives over this. Okay, so translate to p-divisible groups. This means that the pullback of the p-divisible group here is the same as the p-divisible group here. I'm using Tate's theorem now that p-divisible groups are determined by the generic fiber. They are determined by the étale system, right? But now, both of these are versal. So you have something that's versal here, you pull it back, and it stays versal. This means you have to have a formal local isomorphism between the corresponding points here and here. So you combine this with Zariski's main theorem, and you get the proof. So, right? So they are normal, same dimension, proper formal local isomorphism. And so finished by Zariski's main theorem. So these are local, formal local isomorphism. Completes the proof, essentially. Okay, so of course the difficulty here is to, if you have the two models coming from different embeddings, you have to compare that the displays are the same, regardless of what embedding you used. That's why the hard work was done before. So I guess that's all. Thank you.
Any questions? same group, one
Yeah.
inside the other. Do you have an actual map from your integral model for one to the integral model for the other?
Not so obviously. So no, it's not a stupid question. No. No. I think you can make this, but I have to be sure. I mean, I don't think it's an obvious thing. Because the way they are given by the Zariski closure, you have to find compatible kind of embeddings in Ziegel space or whatnot. So no, that's a good question, actually. But I expect in many cases you can work this out. I mean, somehow, it's an explicit case you can probably.
So you couldn't say take the Zariski closure, sorry, the normalization of one and the other and show it.
No, but this usually doesn't work because when you change Paregorics, the maps are not finite.
Yes.
Okay.
Yeah, so
So it's not so.
I don't think so.